Hello, this is Analysis of Algorithms. We're dealing with Chapter 12, which is about binary search trees. We're going to do these problems. And as always with the homeworks, first do the homeworks on your own and then check the answers here. Okay, great. So let's start with section 12.1. It's a clever question. It gives you 10 numbers, 1, 4, 5, 10, 16, 17, 21. Okay, these are, and it says of keys, draw a binary search tree of heights 2, 3, 4, 5, and 6. Okay, so they want to show you that the same numbers can be both in a good tree and a bad tree, etc., etc. So obviously the good trees are the short trees, the short and stout trees, and the bad trees are not. So rather than wasting time doing it, I did it. This is a level 2, 0, 1, 2. This is all pushed up. This is level 3. 1, 2, 0, 1, 2, 3. This is level 4. Okay, and you keep on doing this, just turn this like this, and you have something of level 5. 1, 2, 3, 4, 5, 6. I'm sorry, 0, 1, 2, 3, 4, 5. And this one, just having start from 1, doing it in order, this long snake is of level 6. 0, 1, 2, 3, 6 to 6. So again, obviously there are many different answers to this. But the point is that the same nodes, the same things, can show up in many different ways, and we like them when they're short. That's the point. Okay, good. Next. Question number 2. What is the difference between a binary search tree property and a min-heap property? Okay. Can the min-heap property be used to print out the keys in an n node tree in sorted order in O of n times? Show how or explain why not. Okay, and the answer is, let's do this. A min-heap, okay, usually in class we talk about a max heap, but a min-heap is where the father, okay, is smaller than his two children. Smaller than his two children. So we're going to have something like 5, 10, 12. Okay? That's a min-heap. The father is smaller than his two children. Okay. Now, the problem is there's no order to the left child or the right child. So this is the same, also a min-heap. Okay? And so is this. Well, it's not a min-heap. Okay, that's not a heap, whatever. Okay, so the problem is there's too much looseness going on with a min-heap because we don't have it that well structured. As opposed to that, if we were to do this not with a min-heap, but with a binary search tree, it looks like this. 10, okay, and here's 5, and here's 12. Another example is here's 5, here's 10, this is not a min-heap, and this is 12. Okay? Anyways, it's much more rigorous of what it can be. Okay? And we can do an in-order search or for these things, and we'll get it out in sorted order. But not for these things. Okay? The reason is because there's not enough structure. There's a lot of things that can go on. For example, in here, I think an uncle can be, well, you can say some things about uncles. Here you can't say about uncles and uncles and nephews of how their relation is. So it's not strict enough, a min-heap. Okay? Let's just say the difference. A min-heap, the father is smaller than its two children. Nothing about left and right. For a binary search tree, the father is larger than all the children on the left and smaller than all the children on the right. Okay, so that takes care of that. Let's look at number 4. Give a recursive algorithm to perform pre-order and post-order tree walks in O of n time on a tree of n nodes. Let's just remember what we did. In class, we did in order. Okay, and what that means is What that means is first print out what's on the left, then the middle thing is printed out, and then what's more is printed out, so it comes out in order. But we can also do it pre-order or post-order. In other words, first print out the 5, then the 3 and the 10, or post-order, first print out the 3 and the 10, and then put the 5 afterwards. Okay, so it's all a matter of how you're ordering the operations. So let me just do it. Okay, pre-order tree walk. Okay, the main thing is it should be recursive, because most of our algorithms are recursive. If x is not equal to nil, okay, then this is pre-order, so first we do the root, and then we do the left side, and then we do the right side. So it's going to be as follows. Print x dot key, or key of x, depending how you want to write it. Okay, and then recursively pre-order tree walk. I'm doing it following it the way the book does this. X dot left. Okay, pre-order tree walk. Walk x dot right. Okay, so first print the root, then print what's over here, then print what's over here. Okay, that's a pre-order. Pre-order tree walk. Good. Recursive, you see the recursion right here. Okay, good. Let's do the post order. Ha ha ha. We can do this. Post order tree walk. Basically, it goes as follows. First, do post order tree walk on the left. Then do the post order tree walk on the right, and then the root print x dot key. Okay, that's very nice. Okay. Okay, I don't see why, I mean, the numbers don't come out very ordered, but it's still nice. Okay, great. Next. Section 12.2, number 1. Okay. Suppose that we have numbers 1 through 1,000 in a binary search tree, and we want to search for number 363. Which of the following sequences would not be a sequence of nodes examined? Okay? So, it's a cute problem. Okay? And I want to show you how to do it. Okay? So, I want to understand how a binary search tree works. How a binary search in a binary search tree works. You start at the root, and you go this way, and you go this way, and you go this way, and you climb down to the thing that you're looking for. That makes sense. Okay? But what can you say about it when you're climbing down? Well, if you went this way, that means you're never going to go, in other words, you had some number here and you went this way, that means you're never going to go further that way. Okay? In other words, if you have the number 320 and you're going this let me put my back. If you have the number 320 here, okay, and you go this way, I don't know what number you're going to find there, but one thing for sure, you're never going to get a number larger than 320. Okay, so let's say you have 175 here. That's good. Okay, now you can go further here, and let's get 150. Okay, but one thing for sure, since you have 175. You will never get 176. Because his children will never be 176. He is everything to the left of 175. So this is impossible. Okay, so let's do some of the problems that they give us. Okay, start off with 2. That makes sense. It's a bad thing to start off with, but fine. Okay, then you go to 252, which is going to be this way. Okay, then you're going to go to 401, which is this way. That's good. Okay, then you're going to go to 398. Okay, that's still more than him. It's still more than him. It's less than him. You are not allowed to go beyond 401 anymore. Okay, then you're allowed to go to 330. Okay, then you're allowed to go to 344. Okay, that's not more than him. Then 397. That's still not more than him. That's okay. And finally 363, which is more than this. 363. So that's okay. Okay, so that's good. So everything here is kosher. You're not going beyond the bounds of what you're not allowed to. Okay, I want to do, well, let's do them all. Okay, but the answer is C is not legal, and I think E is not legal, but let's do it. Ready? 924, 220, 911. 911 is still within bounds of here, that's okay. Okay, 244, that's okay. That's within bounds of here. 898, that's definitely okay. 898. That's less than these two. Okay, 258, that's more than these two. 362, that's less than these. And then 363. Okay, so everything is within the boundaries. So that's a legal move. Okay, we're going to see where it doesn't work, and then you'll understand how the right way to do it. Okay, so let's do where it doesn't work. So this one doesn't work. 925, that's fine. 202, that's okay. 911, which is 911, which is less than 925, so that's okay. 240, which is more than 202, so that's okay. 912. Okay. How the hell can you have 912 when you moved here? Everything to the left of him is less than 911. How could you have 912? So we can stop right there and we can say this doesn't work. No such sequence can possibly happen right there. So that's very interesting. Okay, they're showing you how this binary search tree actually works. And the way it works is you have to look at all the boundaries beforehand and see that you remain good. I don't have to go further because this is no good already. Okay, let's do the next one. D. 2, 399, 387, 219, still more than 2, 266, that's this way, still less than this boundary, 266, 382, oh, we're getting close, 382, but still we're okay, 381, that's more than that, so that's 381, still good, 278, that's more than this, less than these, so what was that? 278 is this way. and 363. 363 is less than this. 363, 363. Still good. We didn't make one bad move. So that's good. So D is good. Let's do E. So finally E. Let's do E. Okay, let's do it. 935. Okay. Let's try to 278. 347. 621. Still less than 935. 299. 299. That is more than 278. Now, how can we do that? That's illegal. That's illegal. We went from 347 to 621. So we can never go less than 347. 299 is less than 347. No good. Right here is no good. Let's do it with the red color and just say buzz. No good. Right here it's no good. And we can forget about the rest of the problem. Because if that's no good, nothing else will be good. Okay, so let's just go through this again. We went more than 347, and here we're trying to go less than 347. This 299 is not in the right tree of 347. So stop right there. Okay, that takes care of that. Number 2. Write a recursive tree minimum and a recursive tree maximum. Okay, a recursive tree minimum and a recursive tree maximum. Let's just remember what it says. The tree minimum is just keep on going to the right of the tree. The tree maximum is keep on going to the left of the tree. Smaller, smaller, smaller. Tree maximum is keep on going to the right of the tree. So we're going to do that. Okay, let's erase this. Okay, number 2, tree minimum. Tree minimum of x. Okay, if x equals nil, or x dot left equals nil. In other words, if it's empty or there's no children there, or it has no children, return x. Now this is funny. You're sending in a node that's nil. Well, that doesn't have any children for sure, so what's the shortest of nil? Answer, x. So it's going to return nil. It doesn't have a thing. Okay? Else, if you're not returning that, then else what? Tree min of x dot left. Okay? So that always calls the left child, left child, left child, left child until it hits a nil. Okay, and when it hits a nil, it returns it. When he has no left children, when there's no one left less than him, then he returns x. Okay, all right, good. Let's do tree max. Gotta erase some things. You have to rewrite it. I don't have to rewrite it. Okay, what's tree max? Okay, that's where we keep on going to the right, to the right, to the right. So if x is equal to nil, same thing there. Or if x to the right is nil, then return x. Otherwise, tree max of x dot right. That's it. Let's leave it at that. Okay, that's tree max. Okay, good. That's number 2. Number 3. Write the tree predecessor thing. Okay, so this I wrote out before. let's do that. Let's just review a little. In class we did tree successor. What's the tree successor? Okay, the tree successor is, what is the successor of x? It's if you look at everybody bigger than x, the minimum is the tree successor. Okay, now it could be that there's nobody there. If there's nobody to the left of it, then you have to start climbing up. Okay, let's talk about the predecessor, not the successor, the predecessor. The predecessor is that element which, if you look at everybody less than x, if you look at everybody younger than x, the oldest person younger than x is your predecessor. The maximum of those less than it is your predecessor. Okay, so, and again, you might have to climb up the tree, because you might not have, in your predecessor, you might not have anybody to the left, so you might have to climb the tree. And when you climb the tree, the first wrong turn that you make, you have to get it. Okay, so let's write it out. Okay, you should really try to do this on your own. Okay, tree predecessor. Okay, if x dot left is not equal to nil, then return tree max x dot left. Okay, let's just do this. This is the easy part. Okay, but this is the intuitive part. What is the predecessor? Look at everybody before it and find the maximum of everyone before it. That is the predecessor. Okay, so call the tree max and get that. Okay, but things can happen. Okay, there could be nothing to the left of it, which means the predecessor is higher up. So now we have to climb the tree. Here's how we climb the tree. Y equals x dot p. P is the parent. Start climbing. Now y is going to be the father, x is what you're looking at. Now we climb. While y is not equal to nil. Now, how could it be nil? How could y be nil if you're climbing the tree? And the answer is you get to the root. When you climb to the tree, the root's father is nil. Okay? And x equals y dot left. Okay, this is the important thing. Okay, I'll do it in a second. Let me just finish writing. Okay, as long as we're keeping on doing this, then x is equal to y. We're climbing up the tree, so set x, the son, should be the same place where the father is. Okay, and y is equal to y dot p. Move up. Let y, what was the father, should now go to the father's father, the parent of the father. So we're climbing up the tree. Okay, and when we stop here, when you finish, then return y. Okay, so we need to do this for a few minutes and understand it. Basically as follows. You're climbing the tree. Okay, and you're climbing the tree. And you're climbing the tree so that, like this. Here's x, here's y. Okay, and you're climbing the tree, and you're climbing the tree. Now you're looking for the predecessor of him, but he's less than him. I'm sorry. Damn, I'm wrong. Hold on. Here's x, here's y. Okay, you're looking for the predecessor of him. He has no left children, so we have to climb the tree to find it. Okay, and you keep on climbing. Okay, but he is more than, x is more than y. Y is more than x. So we're looking for the predecessor that's younger. Okay, so this is the wrong thing to do. So what we do is, forget about this and we climb the tree. X becomes where y was, and we keep on climbing the tree. That becomes the new y. Okay, but again, y is more than x. We're looking for predecessor, so this doesn't work. So we're going to keep on climbing the tree. X, and we're going to go up to there. And here's y. Okay, at some point, either we hit the root or we make a turn like this. Okay, and so this becomes x, and this becomes y. Okay, now, this is the first time where the father is less than him. And it's the first father that's less than him. And so he is the predecessor of this. So when we finally break out of this, when x is the right child of y, like this, then we break out of it and y is the predecessor. He's the first thing afterwards. Okay, so that's a very nice algorithm. Okay, good. Let's do, I think we're up to 12.2, number 6. Consider a binary tree. This algorithm is going to do exactly what we just did, but for successor. Consider a binary tree whose keys are distinct, so we don't have the same things. Show that if the right subtree of a node x in T is empty and x has a successor y, then y is the lowest ancestor of x whose left child is also an ancestor of x. Okay, so let's erase this because this is talking about a predecessor and question number 6 is talking about a successor. Okay, so let's erase it and let's just, here's x, okay, and we're looking for a successor. So a successor is very simple. It's the minimum of this tree. Okay, it's more than x, but it's the minimum of all the things more than x. Now the question says as follows: what if this doesn't exist? What if that doesn't exist? Now let me read the question again. Consider a binary search tree whose keys are distinct. Show that if the right subtree of a node x is empty and x has a successor, if it has a successor y, then y is the lowest ancestor of x whose left child is also an ancestor of x. Okay, so what we're going to do is we're looking for a successor. And I think what we do is like this. We're going to climb the tree this way. Okay. And the first time we make a move like that, successor, he is more than x. Okay, because x is on the left tree of y. Okay, so this is exactly the reasoning that we did 2 minutes ago, but here we're talking about a successor. Let's read it again. Y is the successor of x, then y is the lowest ancestor of x, whose left child is also an ancestor of x. So here's y dot left, okay, and he's also an ancestor of x. He is a parent of x. Okay, the main point is as follows: y could have y has a parent too. It could be this way, it could be this way. I don't care. But the point is, this is the lowest y, where you first make that first right turn. Okay, so let's go through this. He is here's x, he is less than x, he is less than x, he is less than x, he is more than x. We went this way. It's a first right turn, he is more than x. So that takes care of that. Okay? Good. Okay. Okay. 12.3, number 1. Tree insert. Okay, they want a recursive version of tree insert. It's very simple. How do you insert a node? You start from the top and you climb down. Okay? You climb down till you find the right thing. Okay, and then till you get to a nil, and then you put it in that place. So we're just going to do the same thing. The only thing is, the first part about climbing down, we're going to do it recursively. So that takes care of that. Okay, so we're doing tree insert. Hold on. Recursive. Okay, so let's do it. I'll tell you what these things are in a second. Okay, if x is not nil, okay, what are we doing? We're climbing down the tree till we find nil. So if x is not nil, then we keep on climbing. Question, should we climb this way? Should we climb this way? You have x, should you go this way or should you go this way? Okay, so it goes as follows. If z is not nil, then do the following. If z dot key is less than x dot key, then tree insert recursive x dot left comma z. I'm putting in z. Z is what I'm putting in, and where do I put it in? Okay, hold on. Else tree insert recursive x dot right comma z. Okay? This way or this way, this way or this way. Okay? Finally, the rest of this is exactly like the rest of the thing here. So let's do it. Z dot p. Okay? This is what we're putting in. Okay? Z dot p is equal to y. Now, we have to worry. So here's where we start looking. Father of x. Okay. So when the next time we go into the tree, we're sending the left tree, he becomes the father. We send the right tree, he becomes the father. So we're always passing in. We're not only just passing in the node and going down regularly like we did in the iterative version. In the recursive version, we're giving both pieces of information. Who's the father, who's the son. So I'm telling you who's the father is here, the son is there, and then the thing we're putting in is over here. The rest is just exactly like the other thing, like the iterative, but let's do it. If y equals nil. In other words, how could that be? How could the father of the person you're starting to look for is nil? The answer is if you're starting to look for the root, the father of the root is nil. Okay, so then what do? You do t dot root is equal to z. That means you have nothing there, put z in its right place. Okay? Else if, okay? Otherwise, if it's not the root, then you have to know, should I put it in the left or should I put it in the right? So it goes as follows. Else if z dot key is less than y dot key, okay, then y dot left is equal to z. Otherwise, else y dot right is equal to z. From here to here, it's exactly like that. You can, like we did in class, you can look it up in the class. It's the same thing. You have z, you want to put it in. This helps you find where to put it. Okay, this tells you who z's father is, and the question is, should you put it z, the new thing, should you put it on the left or the right? And that's exactly what this tells you to do. Okay, great. One last question, section 12.3, number 3. Let's read the question. We can sort a given set of n numbers by first building a binary search tree containing those numbers. Okay? Use tree insert repeatedly. Okay? And then printing the numbers in an in-order tree walk. What are the worst and best case running times for this sorting algorithm? So it's a funny algorithm. You take a bunch of numbers and you put them in a binary search tree. And then read through the binary search tree in an in-order way, and you have it in order. So reading through the binary search tree, that's n. That's no problem whatsoever. Okay? But what about setting it up? And the answer is, it's very funny. Well, how much work does it take to set up this binary search tree? Okay, so you're going to throw up a node, you're going to throw up a node, you're going to throw up a node. You're going to throw up n nodes on this binary search tree. You're going to throw up n nodes on this binary search tree. Okay? Okay, what's the worst thing that can happen? What's the best thing that can happen? Well, let's do the best thing. The best thing that can happen is you're throwing up a node one at a time, and each one of those n nodes, okay, the shortest amount of the tree can be is log n. Okay, so in the beginning it's not going to be log n, it's going to be smaller, but as you're throwing it up, the best is log n. So basically, you're throwing up each node, to put it on the tree, you have to climb down the tree to put it in the right place, so that's log of n. Plus, once you have the tree set up, you're going to have to do an in-order search, an in-order printing, and you get that. So that's the best case scenario. But what's the worst case scenario? The worst case scenario is you throw up n things, and the tree is not they're not short and stout, but the tree looks like this. Okay? Now, each time you do it, it's going to have to count down. Okay, so the first one you're going to put over here. The second one you're going to have to count down to there. The third one you're going to have to count down to there. And the fourth one you're going to have to count down to there. This is sum of I equal 1 to n of I, which is n squared plus n divided by 2. Okay, so that's a lot of work. Okay, another thing that can happen is you could do it like that. Okay. So that's n squared work. And then afterwards you have to read through this binary tree. Okay, but the interesting thing is, when do these two bad cases happen? Okay, and the answer is when the original list that you're throwing up is already in sorted order. So it's interesting. When it's not in sorted order, when it's random, then you throw them up on the tree, and the tree will be short and stout. which is very good. And then it's n log n plus n, which is n log n. Doesn't save you that much. But when the tree is almost in order or very close to order, or in order, then the length of the tree that you're going to get is very, very long. And so you're going to have an n squared algorithm. That's an n squared algorithm. So if it's already sorted, that's when the bad thing happens. That's interesting. Anyways, I hope you enjoy it. And I hope you did the problems there yourself. Hold on. We need a presentation. Come here. I want to meet you. Come here.
We did it 100 times.
Okay, so we'll do it one more time. Okay. This is Miriam. She says hello. Say hello.
Hi.
Okay. Say do your homework first and then check your answers here. Okay. She's not going to say it. Thank you very much.